This is lecture 8. Today we will be talking about quantum numbers. So we'll review briefly the orbital. And so right here on the screen, I have a picture of what society kind of thinks of as the atom, right? With the nucleus in the middle and the electrons orbiting around it. But we now know that that view is not true, right? We know that the electrons are just kind of flying all over the place, and they have areas that they're at more likely most of the time. And there's kind of two interpretations that we can actually take of the modern orbital. One is we can think of the electron not as existing in a single space, but as being spread out over the entire standing wave, thinking of the electron kind of as this big fluffy thing. Or we can think of it as a 3D probability distribution of where the electron will be 90% of the time. Now, we're going to start getting into describing orbitals in much more detail. And so we're going to start talking about orbitals in terms of quantum numbers. And each orbital has 3 quantum numbers associated with it. You'll remember last time we looked at some of these orbitals, and we talked about the N, L, and M sub L quantum numbers. And we talked about how those describe the specific orbitals we see, right? This number here on the front, that's the N. The letter, or the first letter, is the L, and the tiny subscript letters are the M sub L. And we talked about how these different values can describe different orbitals. We mentioned briefly also F orbitals and G orbitals. So I didn't actually show you any of these last time. So the F orbitals get even more complicated, and you'll notice their M sub L coding in letters here gets fairly complicated, right? This is the Fz times x squared minus y squared orbital, which is a bit of a mouthful. And right here, this is the Fx times x squared minus 3y squared orbital. So the F orbitals get fairly complicated, and the G orbitals get even more complicated than that. Though we actually rarely talk about G orbitals. And the reason is because they're actually pretty rarely occupied by electrons that we care about. And especially once our atoms start bonding to other atoms to form molecules, talking about G orbitals just becomes fairly pointless. But we do talk about the F orbitals. We don't look at pictures of them quite as much, but we do talk about them. But today what we're going to focus on is the quantum numbers that we use for describing the different orbitals. So I'll give you actually a summary of everything we're going to talk about right here up front, and then we'll go through each of these individually. So the first quantum number we've dealt with quite a bit actually already. The principal quantum number N, right? This is just the basic quantum number. It's integers, whole numbers greater than 0. So it can be 1, 2, 3, 4, etc. N describes what's called our energy level. And we also refer to this as our shell. So the N equals 1 is the N equals 1 shell, the N equals 2 shell, N equals 3 shell. And as you increase in your shell, you're increasing the energy, and you're increasing your average distance from the nucleus. The next term, the L, is our angular momentum quantum number. And L ranges in value from 0 to n minus 1. And so each L value is associated with an n value. Or in other words, each n value has a set of L values. So for example, for n equals 1, L can be 0. For n equals 2, L can be 0, 1. So L describes the shape of your orbital, and your L values are referred to as your subshell. And the L values are coded in a special way. And we'll get more into this in a minute, but L equals 0, we call an s orbital. L equals 1, we call a p orbital. L equals 2, we call a d orbital. L equals 3, we call an f orbital. So those L's are associated with those pictures we were just talking about. And then the magnetic quantum number, M sub L, is a further subset of L. So L is a subset of N, and M sub L is a subset of L. So M sub L values for a given L value can range from values of negative L to positive L. So for example, if N equals 3, then L can equal 0, 1, or 2. If L equals 2, then M sub L can equal -2, -1, 0, 1, or 2. And so the M sub L describes the way your orbital is arranged in space. And then finally, after that, we have our M sub S. And this is actually our spin quantum number. And this actually refers to the electron itself. And M sub S can have a +1/2 or a -1/2 value. So the way to think about this is kind of all like an address for an electron. N is the city it's in, L is the street address, M sub L is the house number, and M sub S is the individual resident. And these are all stacked within each other. And so they all depend on L. So they all depend on N. So the L that we're talking about is referring to an L at a specific N level. The M sub L we're talking about is at a specific L, which is at a specific N. The M sub L, or the M sub S, is at a specific M sub L, which is at a specific L, which is at a specific N. All right, if that's confusing enough for you, we'll spend the rest of this lecture unraveling all of that and talking about it. I actually like to think about this in terms of the poem about going to St. Ives. I don't actually know what this poem's called, but it goes like this. As I was going to St. Ives, I met a man with 7 wives. Each wife had 7 sacks. Each sack had 7 cats. Each cat had 7 kids. Kids, cats, sacks, and wives. How many were going to St. Ives? The reason I like to point this out here is because if we think of N as the number of wives, well, each wife had 7 sacks. And so we can think of the sacks as L, and each sack had 7 cats, which is M sub L, and each cat had 7 kits, which is, we can think of as M sub S, right? So you can see, I'm pointing this out so that we're getting this idea of stacking. There's different N values, and each N value has its own L values, and each L value has its own M sub L values, and each M sub L value has its 2 M sub S values. Now, of course, the question here, this actual poem, inspires you to try and do a really complicated math problem. But of course, the answer of how many people were going to St. Ives is just 1, because I was the one going to St. Ives. And it never actually says where the man with all the wives with all the cats is going. Seems like an insane group. We should not have that many cats. All right, so let's talk about N. Nothing has changed about N since the last time we talked about it. This is just our principal quantum number. It describes the energy level we're at. It also describes now how far away from the nucleus we are, but it's still just our principal quantum number. And it can range in value from 1 upward. And it has to be whole, integer, value, etc. So we're still interpreting this the same way as we did with the original Bohr model. So we've expanded the Bohr model now. We've called electrons waves. So we're dealing with this new world. But N is still just the quantum number that describes which shell we're, or which N value. So this is a bit of a review question, but if a hydrogen atom absorbs a photon, what happens to the principal quantum number N of the electron? Does it increase, decrease, or does it stay the same? You can pause the video if you want. But of course, when you absorb a photon, you're increasing in energy, you're going up, so your N value also is going up. So you're going from N equals 1 to 2, or N equals 1 to 3, etc. All right, so that's N. Now let's talk about the L term. Angular momentum, or the angular momentum quantum number, describes the shape of our orbital. And that's a little bit of a broad statement because, for example, some of the d orbitals have 4 lobes, some have 2 with a donut, but L is still describing something about the shape. And we'll get more into that later. but our L values range from 0 to n minus 1. And so if we say n equals 2, if we're dealing with the n equals 2 shell, then you're going to have L values of 0 and 1. And these L values correspond to different orbital types. Now, for an example, if you have n different values of L, or that's another way of saying that L ranges from 0 to n minus 1. So if you have n equals 2, then you have values for L of 0 and 1. There's 2 numbers, right? So for example, if n equals 5, then you can have L equals 0, 1, 2, 3, and 4 there. Now we have a special code for our L values, which I've already introduced a little bit, but for L equals 0, we call that an s orbital. That's our spherical orbital. An s actually doesn't stand for spherical, but we'll talk about that in a sec. L equals 1 is your p orbital. That's your double lobe orbital. L equals 2 is your d orbital, which is your four lobes. And L equals 3 is F. And so F is those first set of really complicated orbitals. And then there's G, etc. So this SPDF nomenclature actually comes from when scientists were initially describing spectral lines, and they would describe them as sharp, principal, diffuse, and fundamental. And now those have been associated with individual orbital types. So while you don't need to remember that bit of history, you do need to memorize this relationship of L equals 0 being S, L equaling 1 being P, L equaling 2 being D, L equaling 3 being F. And then beyond that, we just go in alphabetical order with the exception of J. So there's S, P, D, F, G, H, I, K, L orbitals. But the further in the alphabet you get, the more theoretical those get, less practical in application, or the less likely they're actually to be occupied in real life. All right, so this is our angular momentum quantum number. Let's talk just a little bit more about this, just so we really drive this point in. So what I'm saying is for n equals 1, L equals 0. So we only have s orbitals at the n equals 1 level, right? And it's this guy. For n equals 2, L equals 0 and 1. We're not saying L equals 0 or 1. We're saying that there are L values of 0 and 1 at the n equals 2 level. So L equals 0 corresponds to our s orbitals. So there is a 2s orbital. And L equals 1 corresponds to our p orbitals. So that's where we get our 2p orbitals. For n equals 3, L equals 0, 1, and 2. 0 corresponds to S, 1 corresponds to P, 2 corresponds to D. So at n equals 3, you're going to have S, P, and D orbitals. And then for n equals 4, L can equal 0, 1, 2, and 3, or rather it does equal 0, 1, 2, and 3. So you have S, P, D, and F orbitals at n equals 4. All right, let's see how you're doing with this idea. I'm going to ask, what is the name of a subshell with n equals 2 and L equals 1? Go ahead and pause the video and try and figure that out. All right, so what we said, right, this first number in here is our principal quantum number. So that's n equals 2. And so it's going to either be B or C. Then we have L equals 1. So let's see, S, P, D, F. S is 0, P is 1. So we're looking for a 2p orbital right there. And notice I didn't put 2px, 2py because we're talking about the subshell, which is talking about the specific orbital type, not the specific orbital itself. Just to talk about the specific orbital itself, we're going to have to use the next quantum number, the magnetic quantum number, which really just describes which direction this is facing in. And when you get into more complicated orbitals like d and f orbitals, it can also describe funky shapes that you get. So m sub l values exist from a value of negative L to positive L. So if you have an L value of 2, you have m sub L values of -2, -1, 0, 1, and 2. Which means if you do the math there, if you count that up, you get 2L plus 1 different values for m sub L. So if you have one L value, then 2 times 1 is 2 plus 1, so you have 3 m sub L values. If L equals 3, then you have 7 m sub L values. For example, the 2p orbital, which has an L equal 1 value, has 2 times 1 plus 1 m sub L value. So it has 3 m sub L values. And those are -1, 0, and 1. And we code those as x, y, and z. So up here I have the 2py, 2px, and 2pz orbitals. Now you don't necessarily have to remember the m sub L -1, 0, 1 coding relating to x, y, z. You certainly don't have to memorize the d or f coding. What you really need to understand is what m sub L means, how it relates to L, and how it relates to the orientation of the orbital. So now we have our 3 quantum numbers that describe an individual orbital. And so 1 n, L, and m sub L combination gives you 1 orbital. Or in other words, this is the address of one house. So we have our city, our street, and our house number here, and we have our 1 orbital. And the number of m sub L values equals the number of orbitals in the subshell. So in your subshell, you're going to have 2 times L plus 1 orbitals. All right, so let's talk about these orbitals now. We're going to go back a little bit to the Bohr model and tell you something I didn't tell you about the Bohr model. So in Bohr's model, he figured out how many electrons could fit at every n value. So he figured out that at n equals 1, you can only fit 2 electrons at n equals 1 at a time. If you want to go to the n equals 2 shell, you can fit 8 electrons in that shell at a time. The n equals 3 shell, you can fit 18 electrons. At n equals 4, you can fit 32. So at any n shell, you can fit 2 times n squared electrons. So we can take that value now and we can figure out how many electrons we can put in each orbital based on what we just learned. So now what I'm saying is we're going to take all that information we've learned now and we're going to summarize it or consolidate it in a different way than we have before. All right, so based on what Bohr said, at n equals 1, you can have 2 electrons. At n equals 2, you have 8. N equals 3, you have 18 electrons. Now, how many orbitals do we have at each n level? Well, at n equals 1, L only equals 0. And when L equals 0, m sub L only equals 0, because you remember m sub L ranges from -L to positive L. So m sub L ranges from -0 to 0, which is just 0. So it has 1 orbital. At n equals 1, we have the 1s orbital. But at n equals 2, right, we have the L equals 0 and L equals 1 values. So when L equals 0, m sub L still equals 0, and that's talking about our 2s orbital, right? Because L equals 0 is referring to an s orbital. When L equals 1, then we have m sub L equaling -1, 0, and 1, which gives us our 3 2p orbitals, gives us our 2px, 2py, 2pz. So at n equals 1, we have 1 orbital. At n equals 2, we have 4 orbitals. And then at n equals 3, we have L being 0, 1, and 2. When L is 0, we have our s orbital. So at n equals 3, it has a 3s orbital. When L equals 1, we have our 3 p orbitals. So we have the 3px, 3py, and the 3pz. And when L equals 2, we actually have 5 d orbitals. So we have the 3d squared and all these other guys. I don't even want to say their names. So at each n value, we have n squared orbitals. So at n equals 1, we have 1 squared or 1 orbital. At n equals 2, we have 2 squared or 4 orbitals. At n equals 3, we have 3 squared or 9 total orbitals present. Now that means, or so what we're saying is that there are twice as many electrons as orbitals. So that must mean there's 2 electrons in each orbital. But why 2? Why can we actually have 2 electrons in the same orbital? Why don't they try and spit each other out? And this brings us to that last quantum number, the m sub s. So m sub s, that s stands for spin. And m sub s describes the spin of our electrons. The idea here is that when you take a charged particle and you spin it in a circle, you create a magnetic field. And so if you spin your particle clockwise, you get a magnetic field facing one direction. But if you spin counterclockwise, your field faces the opposite direction. And this is known. If you take something charged and spin it at the macroscopic scale, you see this too. And actually, if you do the reverse, if you take a magnet and spin it through some wires, you can actually get electron flow in there as well. That's how electric motors work. But now we're saying that electrons can spin in one of 2 ways, and then they can have a magnet pointing in one of 2 directions. And so they get a magnetic spin quantum number of +1/2 and -1/2. All our other quantum numbers have been whole numbers. So why are we going to +1/2 and -1/2? Well, the reason is because we want these to be opposite in sign, and we like our quantum numbers to differ from one another by a value of 1. And so for the sake of simplicity, we put them at +1/2 and -1/2, because those are the only values where they can be equal in intensity, opposite in sign, and be spaced by a value of 1. It seems like a bit of complicated logic there, but it's actually really useful for quantum mechanics calculations. It just simplifies the idea. But you can either have a positive or negative spin, which would result in either a north or south facing magnet. So what we're saying now is these electrons have opposite magnetic spins, and because of that, even though they have the same electric charge, they're still trying to repel each other electrically. They have opposite magnetic moments or magnetic spins, and so they are attracted to each other slightly through this magnetism. They're still repelled more by the electrostatic interaction than they are attracted to each other, but there is some attraction. And so that's why 2 electrons can occupy the same orbital at the same time, is because this small amount of attraction lets them do that. So now that we've gone through all 4 of our quantum numbers, we can finally introduce what's called the Pauli exclusion principle. And the Pauli exclusion principle says that no 2 electrons in the same atom can have the same quantum numbers. What this means is each electron has a unique set of 4 quantum numbers. So an N, L, M sub L, and M sub S values, right? So the N is the street name, or sorry, the N is the city number, the L is the street name, the M sub L is the house number, and then the M sub S is the actual occupant, the address, or the letter is addressed to, right? So 2 electrons occupy each orbital with opposite M sub S values. When this happens, we describe these as paired electrons. So you get 2 paired electrons in a single orbital that are interacting with each other in a magnetic way. All right, let's try and review everything we've covered so far all in one question with this guy. How many electrons can be in the 3D subshell? Hint, how many 3D orbitals are there and how many electrons per orbital. Go ahead and pause the video now and try and figure this out. Okay, we have from the D in 3D, we can say that we're at L equals 2. From the L equals 2, we know we have M sub L values that range from -2 to +2. So -2, -1, 0, 1, 2. So that's 5 different orbitals. And we know there's 2 electrons in each orbital, which gives us 10 electrons total. All right, so we've talked about N, which is our principal quantum number, describes which shell we're in. L, our angular momentum value, which we code as SP, D, and F. That's our subshell value, talks about the shape of our orbital. We've got the magnetic quantum number, M sub L, and that is going to range in values from -L to +L, and it's going to refer to our spatial orientation of the orbital. And we have our M sub S, which is our spin quantum number, and that has values of +1/2 and -1/2. Each electron has its own list of 4 quantum numbers. All right, so that is quantum numbers. And then next time, we'll ask the question, why do orbitals have such funny shapes?